Okay, this is part two of our notes. The first part, which you should have already done, is on simple mechanisms, simple machines, levers, a wheel and axle, and a pulley. This part is continuing with simple machines, but it's inclined plane wedges and screws, which are kind of all related to each other, which is why they're together. So for our notes today, remember you're following the outline, which is found on the website. This one's pretty short, and you'll notice that it's pretty similar to the other one, so it shouldn't take you very long. In fact, the PowerPoint, which is in Google Classroom, you'll notice the first like 10 slides are the same. So we've got our simple machines, how to calculate mechanical advantage, the magic number of 1 for mechanical advantage. Anything that's greater than 1 means that we're applying less force. Anything less than 1 means we're applying greater force, but we're making up for that with less distance. So we're going to take a look at inclined planes and how to calculate the IMA and AMA for both. An inclined plane is a flat surface that lifts up off the ground. If we were to lift something straight up off the ground or to go up the inclined plane, we're going to go up the same amount of distance. So what we do here is we are going an extra amount of distance, but we're reducing the amount of force. And again, we talked about if we calculate work, work is always the same, or at least really close if we ignore friction. Friction makes it a little bit different, but the amount of work is always the same. It's the force and the distance that we're changing. So to calculate the IMA, the ideal mechanical advantage, we're going to take our effort distance over our resistance distance. So our effort distance is the distance we are moving something up our inclined plane, and the resistance distance is how high we would be lifting it off the ground. So in this case, they call this the slope, which is bad because it makes you think of rise over run, like something you'd learn in algebra, but that is not what they're talking about. They're just saying the distance that we go up the slope, up the inclined plane, is on the top, and the height is our resistance distance, and that goes on the bottom. So in this case, it's going to be 15 divided by 4, and 15 divided by 4 gives us a mechanical advantage of 3.8. So remember that's over 1, so that means it makes it easier. And anytime we make something easier, that means we're spreading it over a longer distance. The actual mechanical advantage, we need forces. So we're going to have our resistance force divided by our effort force. So our resistance force would be the force that it would take to lift something straight up. Or in this case, it's just how much the object actually weighs. Our effort force is going to be the force that it takes to pull something up the ramp. So you can imagine if you had to pull something up the ramp, you're not pulling the entire mass of the object. It's going to be much less. So our effort force is always going to be less than our resistance force. So 50 divided by 20 is 2.5. So in real life, our mechanical advantage is 2.5, which is a little bit less than our calculated ideal. And the difference between the two is friction. So there's friction that's taking away some of that mechanical advantage and making it a little bit harder than it should be. So if we want to see how efficient our inclined plane is, we know what it's supposed to be, and we know what it actually is. So our actual mechanical advantage was 2.5. Our ideal was 3.75. We divide it, we get 67%. A wedge is basically two inclined planes put together. So imagine we split this in half. We got an inclined plane and inclined plane. So the length of the wedge and the width of the wedge is what we're going to need for our calculations. So if you imagine if we put this on its side, this is our slope, and this is the height, or the amount of space that we are going to be moving an object. So our effort distance is the same as inclined plane. This is our effort distance, and our resistance distance is here. So imagine if we had a really thin wedge, it'd be much easier than if we had a really thick wedge, because the thicker it is, then we have to move it or split it apart more. So the thinner it is, the smaller our resistance would be. So for this one, it's going to be our effort divided by our effort distance divided by our resistance distance. So it's going to be 10 divided by 3, which gives us 3.3. So that is our ideal mechanical advantage. When we talk about forces, so our 250-pound force down is going to give us 700 pounds of force outwards. So that gives us our FR, which is our resistance force, is 700. Our effort force is 250. So 700 divided by 250 is 2.8. And we're going to calculate the efficiency again. So our actual is 2.8. Our calculated was 3.3. That gives us an efficiency of 84%. A screw is actually a couple different simple machines. It's an inclined plane that's wrapped around a cylinder. So imagine if we took a screw and just straightened it out, we would just have a really long inclined plane. So when we wrap it around a cylinder, then it's a compact inclined plane. So you can think of it as a wheel and axle as well. So screws are helpful because they change a spinning or rotary motion into linear motion. So you spin it and it goes up or down. And then obviously we use it for fastening things, and it has a large mechanical advantage. So screws are useful with the fact that they are very high with mechanical advantage. But we lose a lot to friction. We're usually cramming screws in tight places, and so that means there's a lot of friction. So we lose a lot of that mechanical advantage to friction. So all screws have some kind of thread information, and so you're going to have the ability to look at a screw and look at its set of numbers and be able to tell what it all means. So this screw right here has a diameter of 1/2 inch, so that's the distance of the threaded part. The threads per inch is 13. That's what the second number means. So if you took 1 inch of the screw and counted the number of little ridges, there should be 13 threads. And then this describes the type of thread, if it's a coarse or a fine thread. I think there's a few other distinctions, but we're not going to worry too much about the last one. Just the first two numbers are important to us. The pitch is the distance between the threads. So if you imagine if we have a lot of threads in an inch, so our threads per inch count, then our pitch would have to be pretty small. If we have a big pitch, then that means there's more space between the threads, which means we've got a fewer number of threads per inch. So the pitch and the threads per inch count, are related to each other. They're actually opposites or reciprocals. So if we have 13 threads per inch, then the pitch is 1 for 13, or 1 divided by 13 of an inch. So how far will a screw with 13 threads per inch move linearly if we turn it 1 full rotation? So it's going to turn 1/13 of an inch, because there's 1 pitch for 13 inches, or for 1 inch. Sorry, that was a lot of words there. So hopefully that makes sense. If not, I can clarify. So for our mechanical advantage, this one's a little bit different. The rest of these are pretty straightforward. This one's a little tougher. So we need to know our effort distance and our resistance distance. So our effort distance is 1 rotation of the screw, and so we'll call that the circumference. The resistance distance is the linear distance traveled during 1 rotation of the effort arm, which is also the pitch. So from the numbers that were given, this is the diameter, so we should be able to figure out the circumference, and this is the the threads per inch. So from there, we should be able to figure out the pitch. So for the ideal mechanical advantage, it's the circumference divided by the pitch, just like we saw here. So circumference is 2 times pi times r, and pitch will represent as p. So if the if we're going to calculate the IMA of a screw, the one that's up here, if the effort applied is 8 inches on an 8-inch long wrench, what would it be? So the circumference of our effort is going to be, or the radius, excuse me, of our effort, because the wrench is 8 inches long. So that's going to be our radius, because if we had a longer wrench, that would make this a lot easier. A shorter wrench makes this a lot harder. So 8 is going to be our radius. And then in this particular case, we have 20 threads per inch, so the pitch is going to be 1 over 20. So then from there, we just do the math. And this is our number. It's 1 times 10 to the third, or 1,000. 1,005 is what they got. So that is the mechanical advantage. So remember, the more the number is higher than 1, the less force we're using, and we're sacrificing that for distance. So screws, we have to spin the screw a long time to get it to move just a small amount, but we have a large mechanical advantage. The actual, so we're going to, same as before, we're going to take our force, resistance force divided by our effort force. So if we measured the amount of force that the screw is pushing down, it's 1,200 pounds, but the force it takes to spin it is only 35 pounds. So that gives us an AMA of 34. So the efficiency is going to be really bad. 34 divided by 1,000 is only about 3.4%. So this screw is really inefficient. We lost a lot of energy to friction, but we're also able to magnify our force quite a bit. The last thing is a compound machine. So once we master each of the individual simple machines, we're going to start to put a few together to make a compound machine. And when we want to calculate the mechanical advantage of a large machine, we take the mechanical advantage of the first simple machine and the mechanical advantage of the second, and we just keep multiplying them all together. So if we had a simple machine that had a screw and inclined plane and all the things that we looked at, we would just multiply them all together, and that would give us our total mechanical advantage. So that will be our next big topic. So for right now, we're just concerned about being able to calculate the mechanical advantage of each individual simple machine. Okay, thank you so much, and good luck.